Alright everybody, welcome back to another video. This is business calculus, more optimization problems. So this video, the video before this one that I posted, business calculus optimization, it's one section, and then in the business calculus book, this section is the next one. It's just more problems. They're a little more difficult, so let's see how it goes. All right, let's get started. It says the highway department is planning to build a picnic park for motorists along a major highway. The park is to be rectangular with an area of 5,000 square yards and is to be fenced off on the three sides not adjacent to the highway. What is the least amount of fencing required for this job? How long and wide should the park be for the fencing to be minimized? All right, so we've got a highway right here, and we are going to fence in an area here. And we can call this X, we can call this Y, and this Y. And it doesn't matter if you call this Y and these two sides X. Doesn't make any difference. But we don't need any fencing right here. So this area here needs to be 5,000 square yards, but we want to use as little fence as possible to do that. All right, so we want to minimize what? The amount of fencing we use. So that's the distance around here. We'll just call that P for the perimeter. You can call it whatever you want. P, F, C, it doesn't matter. But we'll just call it P. So we get that is equal to X plus 2y. So I've got X plus Y, which is X plus 2y. Now, notice what we have here is we've got a function here in terms of X and Y. Well, the whole point of this is we want to get it all in terms of one variable. So they have to give us some more information so we can get it all in terms of one variable. So let's look back in the problem and see what they tell us. It says the park is to be rectangular with an area of 5,000 square meters. So we know we want the area to be 5,000. So we know 5,000, that's the area. Well, what's the area of a rectangle? Length times width, or X times Y. And what we can do here is we can solve this for Y, and you could solve it for X if you wanted to. It doesn't matter, okay? And so we're going to take this and plug it in for Y. All right, so all we did is we replaced the Y with 5,000 over X. And so that's going to give me X plus 10,000 over X. All right. So now let's take the derivative. So P prime is 1 minus 10,000 over X squared. Now, I talked about this in the previous video, taking the derivative of a number over X. I'll go ahead and explain it again. All right, so just forget about the problem right now. Let's just focus on this derivative of 1 over X. So remember, you can write this as Y equals X to the negative 1. So Y prime is negative 1 times X to the negative 2. Y prime is negative 1 over X squared. And it's the same thing as if you have some number, say some number C. C just represents any number. Then we have Y equals CX to the negative 1. And so Y prime is negative CX to the negative 2. And so y prime is equal to negative c over x squared. And that's where this comes from. So what I would do is just memorize. If you're taking the derivative of 1 over x, then the derivative is just negative 1 over x squared. If you have a number over x, it's just negative that number over x squared. Okay? And if you can't remember that, then you can go through this to get it. Go off to the side and do it. Okay? We'll probably have to do that on some of these problems, go off to the side and do derivatives to parts of problems. And that's fine if you do that. Okay? All right, so now what do? Well, we've got to take the derivative, set it equal to 0. So 1 equals 10,000 over x squared. And so x squared equals 10,000. X is equal to 100. Now, I do want you to keep in mind that when we do square root this, we do actually get x is plus or minus 100. But, I mean, for this problem, x has to be greater than 0 because you're not going to have a side with length negative. All right, so we get x is equal to 100. So y is equal to, well, now we take the 100, plug it in for x. So y is 5,000 over 100, which is 50. So our dimensions would be 100 yards by 50 yards. There's your answer. So this would be 100, and each of the sides would be 50. Okay? So that's not too bad. So that's basically how pretty much most of these work. Let's look at this one. We've got a cylindrical can is to be constructed to hold a fixed volume of liquid. The cost of the material used for the top and bottom of the can is 3 cents per square inch, and the cost of the material used for the curved side is 2 cents per square inch. Use calculus to derive a simple relationship between the radius and height of the can that is the least costly to construct. All right, so if we look at this, let's just go ahead and draw us a can here. See if we can draw a decent one. All right, so there's our can, and we will label this the radius, and we will label this the height. All right. Now, they tell us we have a fixed volume of liquid. Okay, and they want us to, where is it? Derive a simple relationship between the radius and height of the can that is the least costly to construct. So we want the cost to be minimized. So basically, you're looking at what do you want to minimize or maximize? That's what you're going to take the derivative of. All right. So we have the cost. We'll just call that C of X. All right. So it's the cost of the top and bottom. The cost of the top and bottom is 3 cents per square inch. Well, what's the area of the top? The area of the top is pi r squared. And we're going to multiply that times 2 because we have 2 of them. We have a top and we have a bottom. And then that area we multiply by 3 because that's how much it costs per square inch, 3 cents. And then we have plus now the cylinder. Okay. Well, what's the area of that cylinder, the surface area of that cylinder? Well, so if you remember, if you have a circular cylinder, all right, let's just draw it over here so I don't mess up my original drawing. All right, so if I take this cylinder, I need the surface area of the of the outside of the can, the side of it. So if I take this and I cut this can in half and open it up and fold it out, it looks something like that. So basically, I'm looking for the area of the rectangle. So this right here, this distance right here represents the height. This distance here, that is the circumference around the circle. Well, what's the circumference of a circle? Well, remember, circumference, the circumference of a circle is pi times the diameter. But notice here, the area of the top and bottom, we have it in terms of r. So we can write the circumference as, instead of pi times the diameter, we can do it pi times, well, what is the diameter? It's 2 times the radius, right? So we can actually write it as 2 pi r for the circumference. So the surface area is 2 pi r, that's this length here, times the height h. And then we multiply that times 2 because it's 2 cents per square inch. Okay? All right. And so now I have my cost function is 6 pi r squared plus 4 pi r h. All right. Now, notice our cost function is in terms of r and h. Well, I want to either get it all in terms of r or all in terms of h. Let's get it all in terms of r. Well, what do we know? Well, they tell us that a cylindrical can is to be constructed to hold a fixed volume of liquid. So we can just say the volume, and we'll call that fixed volume just V naught. If you wanted to just call it V, I guess that would be fine too, but we'll just call it V naught. So what's the volume? Well, remember, the volume of a cylinder, that's the area of the base times the height. So that's pi r squared times h. And so we get h is equal to V naught over pi r squared. So I'm going to replace h with V naught over pi r squared. So C of x is 6 pi r squared plus 4 pi r times V naught over pi r squared. All right, so that's going to give us C of x is equal to 6 pi r squared plus, and then let's see, that's going to be 4 V naught over r. All right, so now taking the derivative, so that C prime of x is equal to 12 pi r minus, now this 4 V naught, that's just a constant. Okay, you just treat that as a number, and remember we talked about it earlier, that's just negative 4 V naught over r squared. And so now we take the 12 pi r minus 4 V naught over r squared equals 0. So 12 pi r equals 4 V naught over r squared. And so that's going to give me r cubed is equal to V naught over 3 pi. Okay, so look, all I did, see the 12 pi, I brought that down to the denominator, brought the r squared up to the numerator. So 4, so see if you get 4 V naught over 12 pi, that cancels. You're left with the 3 pi in the denominator. And so I get r cubed. So I get r is equal to the cube root of V naught over 3 pi. Now I'm not going to go into the detail that this problem has. I'm going to just leave it right here. They want you to do a relationship, derive a simple relationship between the radius and height of the can that is the least costly to construct. I'm just going to leave it here that r is equal to the cube root of this. That would be your radius. So if you get whatever volume they give you, you can just put that volume in there. So, you know, if you want it to be, let's see, what are we in? Inches. If you want the volume to be 1,000 square inches, then you just replace that with 1,000. That'll give you your radius. And then, of course, for the height, you just take this and plug it in for r. So that would be V naught over pi times, and then that would be the cube root of V naught over 3 pi squared. And we'll just leave it right there. Okay. And we can determine that this is a minimum. So if we take the second derivative, so we've got, let's just write the first derivative here. We've got c prime of x is equal to 12 pi r minus 4 v naught over r squared. So if we do the second derivative, double prime of x is equal to 12 pi. And then we're going to take the derivative of this. So just go over to the side and just say y equals 4 v naught over r squared. We'll take the derivative of this part over to the side. And so we're going to get y equals 4 v naught r to the negative 2. So y prime is negative 8 v naught r to the negative 3. So y prime is negative 8 v naught over r cubed. And so since I've got a minus here and then this minus, that's going to make it a plus 8 v naught over r cubed. And we can see that this is going to be positive. Okay. Because, I mean, the volume's positive, the radius is positive, and we got 12 pi plus, so that's going to be positive. So we got a minimum there. All right. All right, let's look at this one. All right. We've got a manufacturer can produce blank video cassettes at a cost of $2 a piece. The cassettes have been selling for $5 a piece, and at this price, consumers have been buying 4,000 cassettes a month. The manufacturer is planning to raise the price of the cassettes and estimates that for each $1 increase in the price, 400 fewer cassettes will be sold each month. At what price should the manufacturer sell the cassettes to maximize profit? All right, so these problems can be kind of tricky to set up. So it's asking us at what price should the manufacturer sell the cassettes to maximize profit. So that's what we're wanting to know. What's the new price we should charge? So what we're going to do is we're going to let x equal the new price at which cassette is sold. That's x. Now, we do want to maximize the profit, so we know we're going to need our profit function. So let's just write down what the profit is. So the profit is the number of cassettes sold times what? Times the profit per cassette. That's the profit. So, all right. So let's get the number of cassettes sold. Number of cassettes sold. So what does that equal? Well, they sell 4,000 each month, right? And for every, let's see, for $5 a piece, consumers have been mad that the manufacturer is planning to raise the price of the cassettes and estimates that for each $1 increase, so every time it increases $1, then 400 fewer cassettes will be sold. So that's going to be the 4,000 sold minus the 400 times X minus 5. All right, so let's just take a look at that. So let's suppose that we sell them for the $5 a piece. Okay, $5 a piece. Because when we sell them for $5 a piece, 4,000 are sold. So if X is 5, that's 0 times 400 is 0. So there's your 4,000. If X is 6, okay, so if we raise the price $1 to $6, 6 minus 5 is 1. 1 times 400 is 400. So there's your 400 fewer. So let's suppose we raise it another dollar. We raise it $2. Then that would mean what? That 800 fewer would be sold. Well, if we raise the price $2, where X would be $7, 7 minus 5 is 2. 2 times 400 is 800. And same thing if you raise it $3. So that would be $8 a piece. 8 minus 5 is 3. 3 times 4 is 1,200. Fewer would be sold. So this is your number sold. Okay. And let's just go ahead and kind of simplify this a little bit. That's going to be 4,000 minus 400x plus, what is that, 2,000? And that's going to be 6,000 minus 400x, which that is going to be 400 times, what is that, 15 minus x, if I factor out a 400. All right, and now we need profit per cassette. So the profit per cassette, well, what is that? What would be the profit per cassette? Well, that would be what? Whatever the new price is minus the $2 it costs to make it. So that would be your new price minus the $2. So your profit function, P of X, remember, here's your profit. Number of cassettes sold times profit per cassette. And so that's going to be 400 times 15 minus x times x minus 2. And now we take the derivative of that. So to take the derivative, p prime of x, we can use the product rule. Let's just look at this as one function, and this as your first function, this one as your second. So the derivative of this, the 4,000 is just tagging along. So the derivative of this, derivative of 15 is 0, derivative of negative x is negative 1, so that's negative 400. And see, look, you can also look at it like this. If you distribute that 4,000 back, that's what? 6,000 minus 400x. What's the derivative of that? Negative 400. And then that would be times x minus 2 plus the derivative of this, which is 1 times 400 times 15 minus x. And so p prime of x, that would equal negative 400x plus 800 plus, and then that's going to be what, 6,000 minus 400x. And so I get P prime of x is equal to, that's going to be what, 6,800 minus 800x. And so P prime of x would be, well, I can factor out a 400, and that would leave me with 17 minus 2x. Okay. And so now let's just come up here. If I take the 400 times 17 minus 2x and set it equal to 0, well, that's 17 minus 2x equals 0. 2x equals 17. X equals 8.5. All right. Now, we've got it. We're going to test the x at 8.5 to see if it's going to be to see if that's going to give us our maximum profit. But remember, if you look at this, x is between 5 and what? 15. Okay, so how do we know that? Well, let's look at this. So it says the cassettes have been selling for $5 a piece. So that was the price that they were just selling for already, and we're going up from there. Okay, so that's x has to be larger than 5, or it can be greater than or equal to 5. But then it has to be less than or equal to 15. The less than or equal to 15, and why is that? Well, because if you look up here, number of cassettes sold, if x is more than 15, we would get a negative number here. So it has to be less than or equal to 15. And so what we're going to do now is we've got a test. Remember in the last section, in the previous video, we did absolute max and min. So we've got to do P of 5, P of 8.5, and P of 15. We got to test it here and at the end points. So we're going to take the 5, the 8.5, and the 15, and you've got to plug them back into that original, into your P of x. And so by doing that, I'm not going to show all the work with that. You can replace each of those x values with those numbers and throw it in your calculator. This gives you 12,000. This gives you 16,900, and this gives you 0. And so you can see there's your maximum profit. And so that would be at $8.50. That's what you would have to sell them for to get your maximum profit. All right. So these problems really aren't bad once you get them set up. But I will say this: that's probably the most difficult is it's just setting them up. It's probably the most difficult. All right, let's look at this. All right, so it says 2 industrial plants, A and B, are located 15 miles apart and emit 75 ppm, that's parts per million, and 300 parts per million of a particular matter, respectively. So plant A emits the 75, plant B the 300. Each plant is surrounded by a restricted area of radius 1 mile in which no housing is allowed. And the concentration of pollutant arriving at any other point Q from each plant decreases with the reciprocal of the distance between the plant and Q. Where should a house be located on a road joining the 2 plants to minimize the total pollutant arriving from both plants? All right, so it's probably helpful to make a little sketch here. So here we've got plant A, here we've got plant B, and here we're going to have some house in the middle. And so let's say that this house is, let's see, what are we in? Miles. Is X miles from that house, and so that means plant B would be 15 minus X miles, because the total is what? 15. And then also keep in mind that this is 1 and this would be 14, right? If this over here started at 0, and this area right here is what we're looking at, because we cannot build a house within 1 mile of each plant anyway. So there's that 1 mile gap right there on each one. All right. So it says that the, where is it? And the concentration of pollutant arriving at any other point Q from each plant decreases with the reciprocal of the distance between the plant and Q. Okay. All right. So here we would have pollutant A. That would be the 75 over X, and the pollutant B is 300 over 15 minus X. So it's the parts per million over the distance from the plant. So that would be, so for plant A, the pollutant was, it emits 75 parts per million. So that's 75 over the distance. And from plant B, that would be 300 parts per million over the distance, which is 15 minus X. Okay. All right. So the total pollutant, if we add the two, that's 75 over X plus 300 over 15 minus X. Now, we take the derivative, P prime. So remember, I told you the derivative of that is negative 75 over X squared. Now we need the derivative of this. And this is one of those ones where, well, just go to the side. Okay, so we come over here, y equals 300 over 15 minus X. So y prime, that's quotient rule. Derivative of 300 is 0 times 15 minus X, minus the derivative of the denominator, which is negative 1 times 300, and that's all over the denominator squared. So y prime would be 300 over 15 minus X, all of that squared. So that would be plus 300 over 15 minus X squared. All right. So we found that. And now, what do we need to do? Well, okay, so we've got this, and let's go ahead and put our conditions on X right here. So what does X have to be between? Well, X is going to be between what? Right? It's going to be between 1 mile and then the 14 miles. Okay? You know, from the starting point. Let's see, what does it say? So we're making our starting point the distance from A. That's what we're looking for, X. That's our distance from A. So it's got to be at least 1, but no more than 14. All right, so now if we take this and set it equal to 0, so if I do negative 75 over X squared plus 300 over 15 minus X, and then that squared equals 0, so I get 300 over 15 minus X squared equals 75 over X squared. All right, so let's go ahead. We've got 300x squared equals 75 times 15 minus x squared. If I divide both sides by 75, I get 4x squared equals 15 minus x, all of that squared. And so that's going to give me 4x squared equals, and if I multiply that out, remember that is 15 minus x times 15 minus x, and I do the full method. So that's 225 minus 30x plus x squared, which that is going to give me 3x squared plus 30x minus 225 equals 0. And then I can divide everything by 3. So that is going to give me x squared plus 10x minus 75 equals 0. That's dividing each one of these by 3. And so then if we factor, that's going to be x plus 15 times x minus 5. And so x equal negative 15 or x equal 5. We know it's not going to be a negative number. Well, we know it's not going to be the negative 15 because it doesn't fall within the distance 1 to 5. And so now we've got to test out P of 1, P of 5, and P of 14. Okay, so we've got to take the 1, the 5, and the 14 and plug it all back into our P function. So we're plugging each one of those in for x, and that's going to give us, that is 96.43 parts per million. This is going to be 45 parts per million, and the 14 is going to be 305.36 parts per million. So we would say 5 miles from plant A, because that was your minimum right there. That was your absolute minimum. All right, so we've got 2 more examples to work, so just hang with me. All right, I think I said we had 2 problems left. I think we got 3. So, but anyway, they're good problems to work. All right, so here it says a cable is to be run from a power plant on one side of a river 900 meters wide to a factory on the other side 3,000 meters downstream. The cost of running the cable under the water is $5 per meter, while the cost over land is $4 per meter. What is the most economical route over which to run the cable? So in other words, how much cable on land, and then where do we need to cross, and then go along the water. All right, so we've got, this is what we've got right here. We've got a river. That's 900 meters wide. We are in meters. Yep, we're in meters. And we have a plant here, and we have a plant here. And so we're going to run along the river and then down to the other plant. Okay? In other words, how much land, how much water. Okay? Now, look at this. Now, if you're taking notes, don't write this part down. We can look at the distance from here to here and the distance from here to here. We can call that x, and so that would be 3,000 minus x, right? And of course, this side here, that's 900. Okay? And you doing that, that's perfectly fine. You can work it like that, no problem. But we need an equation for this. Well, this is just, that's a right angle. This is Pythagorean theorem. So this would equal the square root of 900 squared plus 300 minus x squared. So that would be that distance there. And if you want to use that, if you want to work it like that, that's completely fine. There's nothing wrong with it. Okay? But let me just write that over here. That's the length of this hypotenuse here, labeling this x and this 300 minus x. So let's just erase that for a minute. And let's just look at this. What if instead we label that x, and then this would be 3,000 minus x? Well, then using the Pythagorean theorem, this would be the square root of what? 900 squared plus x squared. Now, doesn't that look much simpler? So that might be some things that you might want to do when you're looking at problems like this. You say, well, I can let this be x, or I can let this be x. Well, set it up, both ways, and see which one's going to be easier to do. Okay? And so now I know that my cost is going to be $5 times number meters water plus 4 times number meters land, right? Because it's $5, where is it? $5 per meter under the water, and it costs over land $4 per meter. So it's 5 times the number of meters that it's running under the water plus 4 times the number of meters it's running on land. And so our cost function, C of x, is equal to 5 times, well, how many meters is it running underwater? Well, that's this distance, right? So that's the square root of 900 squared plus x squared, plus 4 times the number of meters it runs on land, which that's going to be this distance. That's 3,000 minus x. All right. So now let's just go ahead and, well, before we take the derivative, we know that 0 is less than or equal to x, less than or equal to 3,000, because this distance x, it has to be more than 0, but it can't be more than 3,000, because 3,000 is the total distance between the two plants. They tell us that up here in the problem. So let's take the derivative. C prime of x is equal to 5 times. Now, I don't know if you've ever watched any of my videos, my previous videos or anything, but there's a little shortcut for finding the derivative of a square root. So anytime you're taking the derivative of a square root, it's just 2 times whatever that square root is. That goes in the denominator every time. 2 times whatever the square root is, that goes in the denominator. And then you look underneath the square root. What's the derivative underneath the square root? Well, the derivative of 900 squared is 0. The derivative of x squared is 2x. And that's it. And then this, you can take the 4 and distribute it. That would be 120,000 minus 4x. Well, what is 120,000 minus 4x? What's the derivative of that? That's just minus 4. Okay. All right. So now we get our cost is, the 2's cancel. So I'm left with 5x over the square root of 900 squared plus x squared minus 4. And you might be thinking, well, how come he's not squaring the 900 out? If you want to square the 900, you can, but sometimes it helps to not do that, and you will see why in this problem. And so now let's take the 5x over square root 900 squared plus x squared minus 4 equals 0. So I get 5x over the square root of 900 squared plus x squared equals 4. And so if we multiply this up here, so that's going to give me 5x equals 4 square root of 900 squared plus x squared. So that's going to give me the square root 900 squared plus x squared equals 5/4 x. Okay. Well, I'll tell you what. Let's just go ahead. Let's write it 5/4 x equals square root of 900 squared plus x squared, and just leave it like that. All right, and it doesn't matter which side you write it on. That makes no difference. Well, I left myself a bunch of room on this problem, didn't I? But let's go ahead and move on back up. Let's kind of come back up here a little bit. Well, no, we'll keep going down. So I'm going to square both sides. That's 25 over 16x squared equals 900 squared plus x squared. I just squared both sides. And then if I subtract 1x squared to both sides, I'm going to be left with 9 over 16x squared equals 900 squared. And so multiply everything by 16 over 9. So x squared is equal to 900 squared times 16 over 9. So x is equal to square root of 900 squared is 900. Square root of 16 is 4. Square root of 9 is 3. So x is equal to, is it 1200? I believe. Yep, 1200. Now, keep in mind it is plus or minus 1200, but we know it's not going to be negative because that doesn't fall between 0 and 3000. And let's just to remind ourselves, 0x is between 0 and 3000. Okay? And so now, well, what do we have to do here? So we got x is 1200. So I've got to do I've got to do C of 0, C of 1200, and I'm going to do C of 3000. All right, so I'm going to take the 0, the 1200, and the 3000, and those all get plugged back into this. You plug them back into there. And so when you do that, you end up with 16,500, 14,700, and 15,660. So there is your minimum. So it's going to be 1,200 meters from this plant is where you're gonna. That's where you're going to start going on land. And if you want to go from this plant, you just plug the 1200 in here. That'd be 3000 minus 1200. And then that's where you would hit the water and go down. And then the minimum cost, the minimum it's going to cost you. So we would say X is 1,200, and that's meters. And then the minimum cost is going to be 14,700. I don't think they asked for the minimum cost, but I just went ahead and gave it to you anyway. Okay. All right. So that wasn't too bad of a problem. All right. So let's look at the next problem. All right, so we have a bus company will charter a bus that holds 50 people to groups of 35 or more. All right, so it looks like the 50 people to groups of 35 or more, so that means it's going to be, you can have groups from 35 up to 50 total. If a group contains exactly 35 people, each person pays $60. In large groups, everybody's fare is reduced by $1 for each person in excess of 35. Determine the size of the group for which the bus company's revenue will be greatest. Okay, so we're wanting to maximize the revenue. So we know the revenue is equal to the number of people in the group times what? Times the fare per person, how much each person pays. All right. Now, we need to get a variable here. We're going to let x equal something. So could we let x equal the number of people in the group? I guess we could. But we know there's 35. 35 people. That's $60 per person. But for each person you add, you subtract $1 for each person. So don't you think it would make sense to let x equal number of people in excess of 35? Let x represent, okay, is it one person over 35, two people over 35? We'll let x equal that. Okay, so now what do we need? We need the number of people in the group. So number of people in group, well, that's going to be the 35 plus however many extra we have plus the x. And then the fare per person, well, it costs $60. And if we have one person extra, that's going to be 60 minus 1. If we have two people extra, that'll be 60 minus 2 because it's a $1 increase for each additional person. So that would be 60 minus x. So the revenue, so our revenue, R of x, is going to be the 35 plus x times 60 minus x. And we know that x is going to be between 0 and 15. Oh, now how do we know that? Well, we know we're going to have, if a group contains exactly 35 people, so we've got the 35 people, so number of people, that's when x is 0, that would give us our 35 people, and it can go up to 50. So if this right here, the 35 plus x, see the 35 plus x, that's going to be a total of 50. So x would be 15. So that's why it's going from 0 to 15. All right, so now we need the derivative. So the derivative of r, product rule, derivative of the first times the second, plus the derivative of the second, times the first, that's 35. 35 plus x. And so r prime of x would be 60 minus x minus 35 minus x. So I get r prime of x is equal to, that is going to be 25 minus 2x. So we take the, let's just come up here, 25 minus 2x equals 0, 2x equals 25, x equals 12.5. All right, so we've got to test the revenue at 0, 12.5, and 15. Okay, at the x value and the endpoints, and we're going to plug each of those into our revenue function, into this one right here. And so when we do that, we get 2,100. Here we get 2,256.25. And here we get 2,250. So obviously that's our max at 12.5. But we can't have a half a person get on the bus. And if you look at this at the 12.5 and you say x equal 12, x equal 13, if you take the 12 and plug it into the first derivative, you get a positive number, so that's increasing. You take the 13, put it in, you would get a negative number, that's decreasing. So see how it's increasing and then it starts decreasing? Well, if we look at r of 12 and r of 13, so we would want to see, well, would we want to use 12 or 13 people? Would it be best to go down to 12 or go up to 13? Well, if you take the 12 and the 13 and you plug them back into into your revenue function, you actually get 2,256. And when you plug the 13 in, you get 2,256 also. And so your answer would be 12 or 13 people. Either one would give you a maximum revenue. All right. Last problem. All right. This one's kind of, not really complicated, but it is a little bit. All right, it says a bicycle manufacturer buys 6,000 tires a year from a distributor. The ordering fee is $20 per shipment. The storage cost is 96 cents per tire per year. That's the storage cost. And each tire costs $5.75. Suppose that the tires are used at a constant rate throughout the year and that each shipment arrives just as the preceding shipment is being used up. How many tires should the manufacturer order each time to minimize cost? All right, so we want to minimize the cost. So we know that the total cost, well, what is the total cost? It's the storage cost, right? Plus the ordering cost, plus the purchasing cost. Okay. See, because we got an ordering fee of $20, and then we got our purchasing cost. How much does the tires cost? And then you got your storage cost. Okay, how much does it cost for storage? All right, so it's wanting to know how many tires should the manufacturer order. So obviously there we're going to let X equal number of tires in each shipment. That's X. And we've got the ordering cost. Okay, so we need the ordering, storage, and purchasing cost. So the ordering cost is equal to ordering cost per shipment times the number of shipments. That makes sense. How much is each shipment, and how many shipments are you ordering? That's the ordering cost. All right. And then now, and I guess we can go ahead and actually get the ordering cost. So it says 6,000 tires are ordered during the year, and each shipment contains how many tires? X. That's what we're trying to find. how many tires we need in each shipment. So throughout the whole year, it's 6,000 tires. So the ordering cost would equal the 6,000, right, divided by however many tires are in each shipment. That would be for one shipment, and then that would also be times 20 because it's $20 per shipment. And so this would give us 120,000 over X. So there's your ordering cost. Now we need the purchase cost. Well, the purchase cost is the total number of tires times cost per tire, right? So that's easy enough. So purchase cost, that's just the 6,000 times how much is it for each tire? 575. So that's 575, which that is going to give us a total of 34,500. Let me make that look more like a 4 because I'll get confused of it being a 9 later on. And then we have storage cost. This is the one that can get kind of tricky. All right, so let's see. It says the storage cost is 96 cents per tire per year. So as the number of tires change that's being stored, that's going to change your storage price. Okay? But notice what this thing says. It says, let's see, suppose that the tires are used at a constant rate throughout the year and that each shipment arrives just as the preceding shipment is being used up. So we got a full stock. The stock of those tires, it's decreasing at a constant rate, and as soon as that runs out, we're stocked up again, and it starts running down again. So basically, what you can look at it, and not really going to go into detail about how it works like this. This will be something later on in the class when we get into integrals and stuff. But get out of there. So there's your number of tires. And so you're starting out with this number of tires, and what is it doing? It's decreasing at a constant rate. And then notice as soon as it runs out, you're full again, and it's decreasing at a constant rate. And same thing here. It keeps going, and it's decreasing at a constant rate. And this just keeps going on and on. Well, the storage cost, we can just look at it as the average of that. Okay? So remember, these lines going down, that represents the number of tires you have in storage. So we can just look at the average number of tires stored. Okay? So we can look at average number of tires stored times, let me erase this, times and when I say the average number, you've got to understand, see, you're going here, you've got X tires or you've got 0 tires. So what's the average of X and 0? Well, X plus 0 is X, and then you divide it by 2 to find the middle. Let's see, storage cost per tire. That's going to be storage cost per tire. Okay. All right. So the storage cost is equal to average number of tires. So that's going to be X over 2 times the cost, 0.96. So that's going to be 0.48x. All right, so now we're ready for our cost function. All that just to get the cost function. So the cost function is, remember, where is it? Well, I know I wrote, there it is, right here. Let me highlight that. That's kind of hard to see. There's my total cost. So it's the storage cost. The storage cost is 0.48x plus the ordering cost. The ordering cost was this right here. That's the 120,000 over X plus the purchasing cost. Well, where's that purchasing cost? That's 34,500. 34,500. Okay. And I think, did I write it up there? No. Well, I'll write it here. And we know we're going to be between 0 and 6,000, right? It's going to be somewhere between 0 and 6,000. We're either going to have 0 tires or 6,000 tires. Because that's what it told us in the problem. Where is it? Yeah. A bicycle manufacturer buys 6,000 tires a year. All right. So let's look at this. All right. And my bad, I had a little mess up right here. That should be X or 0 less than X. We can't have X can't be 0. All right. So we've got C prime of X is equal to 0.48 minus 120,000 over X squared. We've talked about that a bunch of times. Okay. And so now I've got 0.48 minus 120,000 over X squared equals 0. And so that's going to give me 120,000 over X squared equals 0.48. I just moved this over and then I just, you can swap sides of the equal sign. So let's see, move the X squared up here. So I get X squared equals 120,000 over 0.48. So X is equal, that ends up being X is equal to 500. Okay, and do remember it is plus or minus 500. Okay, and so if you look at this, okay, so let's take a look at this. All right, so that's our minimum, and one thing we can, or that's X equal 500. That's what we need to look at. And so if we take the C double, we can take C double prime of X. So if we take the derivative of this, what is that going to give us as an answer? Well, the derivative of that is 0. And then derivative of this, you can go off to the side. We did the derivative of something like this earlier, but you end up with 240,000 over X cubed. And you can see that this right here, we can plug the 500 in. We do get, that is going to be positive there. Okay, so this does tell us we have an absolute minimum there. And so we would have X equals 500. So when you order in lots of 500, that's when you're going to minimize your cost. And that is all of this video. So this video, along with the one before this, and then also in the description, I will post links to other videos with more optimization problems from business calculus. Okay, so there'll be more examples. They're different than these, so check those videos out also. All right, so I hope that helped. I hope you enjoyed it. Give me a like, share, subscribe, comment, and I will see y'all in the next one. Later.